We've put a lot of effort into representing numbers in different bases, and now we're going to put some of that knowledge to work in representing characters with numbers. So the first thing we're going to do is review the way that we encoded letters of the English alphabet in some of the ciphers that we've used up until now. We're going to recognize that there are many characters that need to be encoded besides just the letters. And then we're going to discuss how characters are represented in computers. We're going to introduce the ASCII character encoding standard, which puts each character with a particular number. And then we're going to relate ASCII to some of the ciphers that we're going to use in the near future. So first thing I want you to do is to recall the shift, decimation, and affine ciphers. One of the things that was really important in these particular ciphers is we needed to represent letters with numbers because we were doing various kinds of computations with them. For the shift we were adding, for the decimation we were multiplying, and for the affine we were doing both adding and multiplying. We used the numbers 0 to 25 for the English alphabet to encode each letter, which was fine for our purposes, but could be quite limiting. For instance, what if we wanted to use punctuation? What if we wanted to encrypt punctuation? What if we wanted to encrypt other symbols? And finally, what if we want to distinguish between capital and lowercase letters? Our 0 to 25 encoding did not allow us to do that. So this will, of course, require more than 26 numbers, and it's going to lead us to ASCII. So how do we represent characters in computers? Well, first of all, we got to think about what computers can do and what computers can understand. Computers can only read zeros and ones. That's their entire world. And so there's actually a special name for such things. Computer science people call the zeros and ones that you have in a computer, or actually zeros and ones in any context, we call those bits. So one thing that you should remember is that every integer can be represented in base 2. That was our binary representation. And since base 2, the digits are 0 and 1, we can represent those numbers as sequences of bits. So we can put a whole bunch of bits together. That gives us a number written in base 2. Now, these sequences of bits have a special name. They're actually called bit strings. And we'll talk about that terminology a little bit more when we use ciphers that encrypt bit strings. But right now, just recognize that a bit string is just a sequence of zeros and ones that you write in a row. So, for instance, if you have, we might encrypt this with our 0 to 25 as A would be 0, B would be 1, C would be 1, 0 because that's 2. D would be 1, 1 because that's the number 3. Then we go to E has to be 1, 0, 0 because we need another place value. 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, and we just sort of keep on going until we get all the letters all the way up to our last one is 11001. So if we wanted to encrypt the letters the way that we have been using in the shift cipher, the decimation cipher, and the affine ciphers, then this is how we might do it. Notice that the biggest one that we have, the biggest number of digits that we have, the biggest number of bits in our bit strings is the letter Z that has 5 digits, 5 bits. And so what we need is we need 5 bits for the numbers, and that would be called a 5-bit code. So here is a 5-bit encoding of the letters of the alphabet. And since they're 5 bits, to make it so that the computer doesn't get confused about how many digits it has to look at before it's finished with the letters, we're just going to give them all 5 digits, right? By putting zeros before the leftmost digits to put it up to 5. So notice that A is not just 0, but it's 0, 0, 0, 0, 0. And C, for instance, is 0, 0, 0, 1, 0. And this makes it easy for the computer to tell when it's at the end of one character and at the beginning of another. It just looks at every 5 digits, if it knows that we're using a 5-bit code. All right, so of course we need more characters than this, so that also means we'll need more bits. We'll need bigger binary numbers to represent all the different characters that we can have. And the nice thing is, every time we add a bit, that doubles the amount of possible numbers. We get, For instance, if you have 1 bit, you get 0 or 1. That's 2 possible numbers. If you have 2 bits, that's actually going to give you 4 possible numbers, 0, 0, 0, 1, 1, 0, and 1, 1. If you have 3 bits, that's going to give you 8 possible numbers. I'll let you count those out and see that those are all the ones that you can have. And you can sort of see a pattern emerging, right? The 2 is 2 to the 1, the 4 is 2 to the 2, the 8 is 2 to the 3. If you have n bits, you're going to have 2 to the n numbers. And so what you need to do is figure out how many characters that you have, and then find another number of n that gives you something that 2 to the n is at least as big as the number of characters that you have. So for ASCII, or at least the original ASCII, is a 7-bit character encoding standard, which means that we encode the characters with numbers using 7 bits, because that's how many we need. So so you know that the ASCII isn't just a random bunch of letters that we toss together. It stands for the American Standard Code for Information Interchange. And it's a 7-bit encoding standard, which means that you have up to 2 to the 7 different characters. And in fact, for ASCII, it has exactly 2 to the 7, which is 128 different characters. Now, this includes lowercase and uppercase letters. Lowercase letters are encrypted with different numbers than the uppercase letters are. It also includes punctuation, like a period or a colon or a comma or an exclamation point. And it includes some other random symbols that you may run into and want to have represented. And then it includes some interesting characters called control characters. Now, these aren't characters that you actually print out like the letters. These are characters that are more commands to, say, devices like a printer that use ASCII. So, for instance, you might have a command that says end of line, that tells the printer that you're at the end of the line, which means it would have to go to the next line to print out the next letter. So you wouldn't actually print out all these characters out. They would just be sent to devices that use ASCII, and then they could interpret them and accept those commands. So I do want to point out that I did put a chart of all the numbers that correspond to each of the characters in the in-class activities. You should look for that. It's not the one that is the in-class activities. It's the other one that's in there. So I'll give you an example, and if you want to see how this works, it's probably a good idea to look at the chart to see what the numbers that are going to go on with things. And I'm going to go ahead and encode the lamest hashtag you will ever see, hashtag hey. Oh, I'm sorry, hashtag hey. I forgot the exclamation point. All right, so first of all, we're going to encrypt our hashtag, and if you look at that on the chart, you'll see that that is represented by the number 01000011. Notice that we put the 0 on the end so that we definitely would have 7 bits. For the H, now this is not just an H, but it's a capital H. And so you have to look for the number that represents capital H's, and that is 1001000. Finally, the E is a lowercase e, so you have to look for the code for the lowercase e, and that is 1100101. And similarly, for the lowercase y, you get 1111001. And next, you would have to encrypt the exclamation point, which is 01000001. And so if you wanted to represent that hashtag to a computer, what you would do is you would take all those bit strings and you would just concatenate them together. So those are just all the bit strings put one after the other. And that may look ugly to you, but to a computer, that looks just like hashtag hey. All right, so just to give you a little look into the near future, we are going to run into 2 ciphers that will be used specifically to encrypt and decrypt bit strings, which seems like a weird thing to do, except that, of course, we have to keep in mind that all plain text messages can be encoded as bit strings, so any cipher that encrypts bit strings also encrypts plain text messages. It also tells us that ciphers that encrypt and decrypt bit strings can be used on English. That means it can be used on English plain text. And the other nice thing is the ciphertext itself, it can be characters, I suppose, although it would be kind of weird that if your ciphertext turned out to be characters that were control characters. But what you can just say is, well, the ciphertext doesn't have to be characters at all. It can just be a bit string itself, and then when you run the decryption on that bit string, then you can encode that as letters. Alright, so now I think you're ready to work on the activities for encoding characters on the PDF file included with this video.